So first I'm going to talk about the physics related component. That will be our rigid bodies and colliders, and then I'm going to move to the interactions, so how we can interact with the physical world. So by applying some forces to your rigid bodies, there's some certain rules you need to obey in order to make your simulation stable and make it look realistic and believable. And then the final, and I hope this will be the most interesting part, this will be dedicated to some of the examples I created for you. So we'll be using joints, we'll create a ragdoll, we'll try to create a slingshot, and some other fun elements that you can create using physics. And the part I started just now, it's about the physics component. So this will be our first part to talk about. And physics component, as I said, they are our main tool to add information to the physics simulation. All right, so here you can see that in your scene, the colliders, they are represented by this green outline. We have different type of colliders. The three main ones, they are based on primitive shapes. There's a box, capsule, and sphere collider. And then we have a mesh collider, and given that you provided with a mesh, it can be any shape. Of course, the lower complexity, the better. Also, if you have any dynamic objects, they would need to be convex. If you provide the mesh collider with the concave shape, you will have to select this one convex and have to convert it to a convex shape. Then we have rigid bodies, and rigid bodies, they are the heart of the physics system, and they enable your game objects to act as physical objects. So the important thing here is that on top of the position, rotation, and scale, rigid body adds velocity and angular velocity. And these are two properties that will allow our objects to move around and react to the physical world. And later we're going to discover what mass, drag, angular drag, and all these different parameters mean and how they change the simulation. So first, here I have two objects colliding with each other, and as you notice, the simulation will obey some basic rules of physics. So here we have the elastic collision, and there is the conservation of momentum. So the object on the right is twice as heavy. So on the collision, he's pushing away the lighter object. So this is really good. But some people I noticed that confuse mass with drag. So mass, the intuition is that for example, a feather, a very light object will fall slower than a heavy object. But what you will discover is that the mass, the rigid bodies, they behave like they would be in a vacuum. So there is no air resistance. So although the object on the right is twice as heavy, it's going to fall exactly with the same speed as the one on the left. Okay, so to avoid confusion, make sure that you understand that the mass is not related to how fast the object moves. So if you want to apply this kind of differentiation, so the lighter object going down slower, the heavier one going down faster, and phenomena like air resistance, they can be simulated with drag. Okay, so this is our second parameter here, and the default value is 0, but if you want your simulation to look more believable, you can set heavier objects to have a smaller drag closer to 0, and some of the reasonable parameters that values that you can set is 0.001 to solid blocks of metal or some heavy objects, and then very light objects like a feather, they should be around in the area of 10. If you set it to higher values, then I mean even 10, it will look very floaty. So what you should try to do is avoid very high values unless this is something you really want to do. And the additional value of drag is that sometimes when things get really, really quick and your objects are moving very fast, colliding with high velocities, drag can actually stabilize your simulation by slightly slowing things down. So later I'm going to show you how to create a rope based on joints, and drag can actually help you to stabilize the simulation slightly. Then we have the angular drag. The default value is 0.05, and it works similar to drag, but instead of velocity, it's being applied to the angular velocity. Here the object on the left, it has the value of 0.05. It's the default one, and the object on the right is 0.5. And what you can see is that the one on the right, it's the value is 10 times larger, and it comes to a standstill much faster. So again, if you have rotating objects that just don't want to stop, then applying angular drag is something you can try. The next two parameters I'm going to show you, they are use gravity and is kinematic. So switching the use gravity, this one here, switching the use gravity on and off will make the object be affected or not affected by gravity. But all the other forces from collision or from your script, they will still affect it. Whereas is kinematic will disable all the external forces, including gravity. So other objects, other rigid bodies, they will still be able to collide with the object, but it will not add any force to your rigid body. So when it's set to kinematic, it's going to be always in the same position, no matter what kind of external forces you apply to it. And this is the one that you should be a little bit careful about to avoid some unsolvable scenarios. I'm going to show you later what I mean by that. To give you a better understanding of the next element I'm going to talk about, I want to very briefly show you how graphics is updated different than physics. So graphics is being updated according to your target frame rate. Most often is set to 60 or 30 frames per second, or FPS, and your frame time may vary. So here I set my time, my desired frame rate to 30 FPS. So this will make one frame to be roughly 33.3 milliseconds to complete. Okay, but this time, as I said, it may slightly vary. So it might be 33.6, 33.2, and so on and so on. So that's why it's very important, for example, if you move objects inside the update function is the one that's being called on every frame. It's so important that on the update function, when it's called, you multiply your variables by time.delta time, so that, you know, although the time varies, you can still produce a smooth motion. Whereas fixed update is a method that you should use to apply changes to, for example, velocities of your rigid body. And the difference here is that, first of all, usually it's called more frequently than update. If it runs faster than update, then it may be that within one frame you have two calls of your fixed update. But if the fixed update takes a little bit longer, then it might be that within one frame you have no physics updates. So unlike the update, when you apply some movement calculations, you don't need to multiply values by delta time. And this is because fixed time step is guaranteed to have exactly the same value every time. Okay, so in a fixed update, if you move your objects or you modify the velocities, you can be sure that from frame to frame, these values will be exactly the same. But with update, for rendering, this is not guaranteed. And the fixed time step is very important to understand interpolation and collision detection. So this would be our next point. So for the interpolation, here I have a slightly different setup. So this is from the project I'm going to show you. I can spawn some projectiles here, and when they hit this box, it's going to spawn 3 different objects. All right, and each of them will have different interpolation value. One will have none, interpolate, and extrapolate. So when I'm running my fixed time step at 0.016, this is roughly updated 60 times per second, you can see that there is virtually no difference to how they behave. Often when you want to increase the stability of your simulation, you might want to decrease this value or increase the number of solver iterations in your player settings. But the problem with that approach is that it uses quite a lot of CPU resources. So to optimize for your CPU performance, we need to keep the fixed time step relatively high, roughly around 30 updates per second, which is a default value. So let me switch to a very extreme case. So this is only for illustration purposes. You normally wouldn't have your fixed time step that high. So here you can clearly see which one is which. So the one here on the top, this one is set to none, meaning that the position won't interpolate. Okay, so it's updated according to the fixed time step, so only 5 times a second his position is being updated. The one in the middle, this one is using interpolate, so you can see that we have this very nice smooth movement, and interpolate is using the information from past 2 frames to interpolate to a new position. Then the last one is set to extrapolate. So extrapolate is slightly different. It's trying to guess the future position based on the last position and the current velocity. So you can see that it can also produce some artifacts like falling through, apparently falling through the floor, although the object didn't really fall through this area. Because it's extrapolating and trying to guess its future position, it appears as if it would for a moment go through the floor. So by default the interpolation is turned off. Commonly rigid bodies interpolation set to be used on a player's character, some other important objects that are visible to your camera. This is because interpolation carries some CPU overhead, and this is why it's recommended to turn it on only on main character of some important objects. So with no interpolation, this is the most performant choice. This might cause some jittery movement, so it's not always the best one. Then we have the interpolate. The interpolate is the smoothest one, but the problem here is that it will always slightly lag behind the actual position. Then we have the extrapolate. Sorry. Then we have the extrapolate, and the extrapolate predicts the current position based on the last position and the current velocity. And as I shown you just now, in some extreme cases, it can make objects appear as if they break through the barriers. The next thing is the collision detection. It's a very important one because your simulation, how it behaves, it really heavily relies on the collision detection. So when you have a collider in the scene and you try to push your object, so here I'm pushing this object very fast to collide with this box. When your colliders are very thick, usually have no problems. However, situation is very different when your barriers are very thin. So this is an effect we call tunneling, and you might notice that the object just penetrates through the barrier and it behaves like there was no collision at all. So this happens because let's imagine that we have an object and it's going with some velocity towards our barrier. So in this physics update, the position is here. In the next update, the position is almost at the barrier. But then at the next physics update, the position of the object is on the other side of the barrier. All right, so our physics system will take a look at this situation and we'll see, hey, this object is already on this side of the barrier, so I'm going to push it and move it as it was moving before. All right, so our object is continuing movement in the same direction. So to account for this, we can set our object to continuous or continuous dynamic. So each rigid body will have this collision detection here, and with setting to continuous or continuous dynamic, our physics system will have higher chance of detecting such collision. but this has some limitations too. So in this scenario, the continuous collision detection doesn't really work well with barriers that have some rotation to it. So if they have some angular velocity, especially if it's very high, then there might be a chance that the collision system will miss this collision. So to fix that, to account for this, we can set the barriers to continuous speculative. And the continuous speculative works much better with this fast rotating objects. And you can see that here the collision was detected correctly. We can't penetrate the barrier anymore. So to sum up, this discrete collision detection is the reasonable default and is the most performant one. But for fast-moving objects, to avoid barrier penetration, we want to probably use the continuous dynamic. And for the objects that collide with these fast-moving objects, we want to go for the continuous. And finally, to account for angular velocity, we can fall back to the continuous speculative, which deals very well with fast rotating objects. Okay, so this is the choice that you need to make when you set your rigid bodies in a scene. Then we have physics materials. So to make some our collisions more interesting and more physically accurate, we can add some physics material to our colliders. And they allow you to modify friction and bounciness of the collision. So in this video you can see that this one here, it has 0 friction when it's going down the slope. The one in the middle has very high friction, so it comes into a halt almost immediately after the simulation starts. And then we have the one with almost 0 friction and high bounciness, so it's almost fully elastic collision here. The physics materials, they are assets that you can create in your project. So in your project you just have to right click, go to create physics material, and then you can add dynamic friction or static friction. Dynamic friction applies to objects that are already moving, static friction to objects that are not currently moving. Then you have the bounciness, and you can set both of them to different combined methods. The default one is average, so it will average two physics materials and take the average, but you can also set it to minimum, maximum, or multiply. So once you have this one created in a project, you can assign it to a material field on your collider, and that's basically it for setting up the physics materials. Next, we can set our colliders to triggers. So this is a very important one. So if you set it to trigger, the collider won't register any collisions, and other objects, other rigid bodies with colliders will be allowed to go through that particular object. But the advantage here is that it will register some additional callbacks. If you have a monobehavior script attached to it, you can receive messages such as on trigger enter, on trigger exit, and on trigger stay. So this is basically a way to notify us when an object is entering this area, when it stays in the area, and when it leaves the area. So triggers are very useful. And finally, we have the constraints. So this is the last portion here. They allow us to disable movement and rotations in certain axes. So for example, if you want your object to be affected by external forces only in the y direction, you could take this one, freeze position X and freeze position Z, and this will basically cancel all the forces that affect this object and basically set the velocity of the X and Z components to 0. And of course you can do the same for the rotations. So X, Y, and Z, you can also freeze the rotation. Alright, with that said, let's take a look at the interactions. So if we keep our physical world just as it is and we don't add any external forces, this would be very uninteresting to our users, right? We need to add some sort of interactions to, or maybe some external forces to move our rigid bodies in a scene. And first such external force that we have enabled by default is the gravity. All right, so here is the default gravity, and the default one is set to be approximately equal to the Earth's gravity, so it's minus 9.81 in the y-axis. And this, very often you might find it to be a little bit boring, because it takes quite a while for this object to come down to collide with the ground. And that's why in many design books, what you see is that good advice is to set the gravity to slightly higher values. So, for example, for your character controller, you can make your character come to collision with the ground a little bit faster. And of course, this is not physically accurate behavior, but very often this is something what your players would expect to have this kind of more dynamic experience. So think about, for example, Mario. In Mario, the main character is accelerating down, I think, around 5 times faster than the real Earth's gravity. And this is actually quite a common practice and gives this more dynamic feel to your simulation. And this can be set here under project settings, physics, gravity, and you can just multiply it by any arbitrary value. You could actually disable the gravity altogether for all the rigid bodies in the scene, and you could add maybe some trigger areas that will have some custom gravity, maybe pulling it to the left or right. So this is something that it's possible to. And of course you can tweak it, you can toggle it to use or not use the gravity on the rigid body by toggling this use gravity field right here. Okay, the one you'll probably use the most throughout your simulation is the add force. So here I have just a very simple stack of 1000 cubes, and they're stacked on each other. And on a mouse click, I instantiate a projectile, and I add force to this projectile to move forward. So with this, you can simulate shooting projectiles, adding velocities and things like that. Let's take a look at the code. So this is something you would usually have in your script, in your monobehavior script. So first you need, of course, the reference to the rigid body, and then you need to call the add force. Okay, and with add force as a first parameter, this would be like a vector 3, and then you can multiply it by. This one is actually not a good example, because usually this would be vector 3. So this would be your direction multiplied by a thrust, right? So I would multiply it by a thrust here as a first parameter, and then the second parameter is the force mode. This one is very important, and I'm going to briefly talk about it in a second. The next one is the apply force at position. So it's very, very similar to the previous one. So you basically apply force to a rigid body. So imagine, let's say I have a boat. Okay, here's the central axis, and let's imagine that this boat has 2 propellers. There's one propeller here and one propeller here, and I could simulate how these propellers would work and how they would affect movement of the boat by applying a force at this position. All right, so at this position I would apply a force moving forward, and this will not only result in pushing the boat forward, but will also add some angular velocity to it. So this is a very useful one. Then finally we have the add torque. So add torque is very simple, and it's just going to add some angular velocity to your rigid body. By default, the collisions the collision detection algorithm, they're not dealing very well with high angular velocities. And this is why by default, what you might find out yourself is we are limited to 7 radians per second. This is a default maximum angular velocity. And this is kind of a reasonable default because you really very rarely want some object to spin faster than that. So yeah, if you want higher angular velocity, you can set the rigid body's maximum angular velocity to higher value, but then if you don't use the speculative collision detection mode, you might miss some collisions and your simulation might be a little bit unstable. Then the final one in this section is the add explosion force. I think this is the most satisfying one to look at. So in a script, you can basically add an external force at certain position, and as the name suggests, it will add this kind of explosion effect. So this is what usually your code will look like. You have the certain position where you want to apply this force. You will get the rigid bodies in the radius, and then for each one of them you would add the external force, this add explosion force with power, position, and radius. The last parameter is the up component. So if your explosion happens here and you have your object rigid body here, instead of applying only force in this direction, it will add some up component to it. So on explosion, your rigid bodies will go slightly up above the ground to create more interesting effect. Something that's not really recommended, but if you're an experienced user, you can manually modify the velocity of your rigid body. As I mentioned before, when you add the force to your objects, you do this with one of the 4 modes. Okay, so when you add force, the mode can be force, acceleration, impulse, or velocity. And if you want to modify the velocity by hand, you can actually do this, although it's not really recommended. You should most of the time you should use the add force. But this is something you can do. You can modify the velocity directly like that. So rigid body dot velocity, and set any value you want there. But on this slide, really what I want you to know is that something that I was not aware at first, but it's important. When you use the acceleration in this equation here, you can see that the acceleration ignores the mass. So there's no mass in the equation here, and the same for the velocity change. And there is no mass here. So if you just want to modify the velocity, I think the easiest one would be to use the velocity change. All right, so this will be resulting only with the delta v, your change in velocity. If you want to propel object very fast forward, maybe when you spawn a bullet and you want to move very fast, then the impulse mode is very good for that purpose. Then one last thing in this section is you usually want to avoid some unsolvable scenarios to get rid of the jitteriness in your simulation. So here, imagine that this cube is a kinematic cube. It's a rigid body, it's set to kinematic, and the same for this one. They both are kinematic, but the rigid body in the middle is a rigid body that's not kinematic. It's reacting to all the collisions. It's affected by gravity, and because it's colliding with these 2 objects at the same time, they will try to apply this push away force to basically push it from the collision state to push it outside. So this kind of scenario is because this rigid body, it's dynamic rigid body, it can't really affect the kinematic one. So if you create this kind of scenarios, you have a lot of jitteriness in your simulation, and it's really something you should try to avoid. Alright, and finally, let's go into the editor and see what kind of interesting gameplay mechanics can we actually create using physics. So I'm going to start with adding some joints, a hinge joint to windmill. So when you collide with it, it will apply some angular velocity to it. Then I'm going to show you how to create this kind of slingshot that will allow you to basically shoot projectiles at your targets. Then I'm going to show you how to apply the configurable joint. This is the most complicated one. I will show you how to use it to create this kind of training dummy that will react to your projectiles, swing a little bit, and then apply some rotation velocity to come back to the original position. Then I'm going to show you how to create this kind of wrecking ball that's connected to a rope. So you can actually chain many joints together, and I'm going to show you how this can be done. And finally, I'm going to show you how to create a ragdoll. This is a very easy one, but the effects that you can achieve are very interesting, and many games actually use ragdolls for the physics simulation. Alright, so these are the examples that we're going to cover, and I'm going to now switch to my Unity editor. Alright, so this entire scene, it actually comes from the creator kit. If you go to Unity Hub, you should be able to go to the Learn tab and get exactly the same asset as I see here. So in the Learn tab, one of the first ones would be the creator kit, and it comes with this kind of Western style town with all different like llama animals, and it has this dummy. It has some interesting, very, very tall cactus. They are your enemies, and there is a main character. His name is Mud Mike. So there are actually quite some nice assets that I used for the purpose of this webinar. The thing I added myself are 3 or 4 scripts. The first one is modifying the... Let me actually mute the audio. The first one is allowing me to modify the camera position to a kind of fly-through mode, so I can just fly around freely around the scene, just like I would be able to do this inside the editor. Okay, and I can also bring this kind of crosshair and try to shoot different things in my scene. Alright, so this is the main modification that I've done. So when I'm shooting these bullets, right, let me just quickly show how this is done. So the shooting script is extremely simple. On update, I'm basically checking here if I can shoot. So I do some basic calculation here. If last time I shot my bullet, is the current time greater than the last time plus 1 over shoot rate? So by default, I set this one to shoot 10 bullets a second. Alright, so this is how I calculate here. I do some object pooling, so I get an object from the object pool, and this is the important bit. So when I get the object, so you could instantiate it, you could get it from your object pool. You get the rigid body, and you just simply apply the force in the forward direction. And here I know exactly what kind of speed I want it to move with. So I'm just getting the forward direction multiplied by speed, and my velocity, my force mode is velocity change. So basically to apply this velocity in the forward direction. All right, so this is my scene. And one thing I want to show you, I want to start with something very simple. So right now, these windmills, they don't have any collision. You can't really interact with them. By default, I think they should have enabled the animation. So I'm going to open that here open that here and see. Yeah, I disabled the animator, but by default they would rotate in counterclockwise, right? But still, there's like no collision. So what I want to show you now is how you can add collision to that and maybe rotate it according to how the collision went. So let me open the prefab. First, I'm going to disable the animator, and I have to parent it somehow. So I need a rigid body that will hold my joint. So my design here is that this object here, this is something that's going to receive the collision, and it's going to put in like a socket inside the joint connected to this rigid body here. Okay, so I'm going to create a rigid body. As a rigid body here. I'm going to set it to kinematic because I don't want it to move. All right, let's just quickly see what will happen if it's not kinematic. If it's not kinematic, it will basically fall off, and yeah, it's not really what we want. So let's set it to kinematic so it doesn't move. And once this one is set, let's add some collision to this object here. All right, so I'm going to add a mesh collider. So it's going to actually, now it applied this very accurate collision, but this is something that shouldn't be really used with dynamic objects. So I'm going to set it to convex. So it's going to approximate how the convex shape with this mesh will look like. All right, and I'm also going to add a rigid body to it. And this one is going to be dynamic. Now, I need a way to connect them two together. Oh, so sorry about that. I think I need to switch to, hang on, share screen. Can you see my Unity? Can you see my Unity editor? So this is a question to people joining on Zoom. Yeah, it's all right now. Sorry guys, I kind of abandoned the Q&A section, but I'm going to go through it after I finish this part. So yeah, let me open that again. So the thing I modified here right now is I added rigid body here to this parent game object, added second rigid body here to the blades of the windmill, and I added mesh collider with the convex shape. All right, now I need a way to connect them together. The easiest one would be, let's take a look what kind of joints do we have. The simplest one is the fixed joint. So the fixed joint will basically make it unmovable. So this is the most boring one. So I'm just going to skip it. I'm not going to use this one. You can take a look. That it will basically just hold it together. It reacts with the collision, but nothing really interesting happens. What we could add though is a break-in force. So right now the break-in force is set to infinity. And we could set it to something like maybe 1000, so that when we shoot a projectile and the projectile collides with the windmill, it's going to detach itself, and this is slightly more interesting. But again, I'm going after the hinge joint. So the hinge joint, as the name says, it's based on a hinge. So here, hinge joint, we are looking for the 3D one. I'm going to, I need to give it a, let me just quickly disable this one. I'm going to give it a connected body. So the connected body is something that will connect this game object to another rigid body. So I need to connect it with the parent object here. All right, the anchor, I'm going to keep it at 0, 0, 0. So it's here at the center of my position. And now I'm not sure if you can see it, but there's this very tiny little arrow that's showing me the axis in which I'll be able to rotate my object. So right now the axis is exactly following the X direction. I need to move it slightly towards the Z and maybe slightly up. So I'm going to, here on the axis, I'm going to modify it to 0, 0, 1. And you can see that now this small arrow is pointing in this direction. It's still kind of off the axis of this object, so I'm going to add some small values to X and Y, maybe 0.25 and 0.25. So it's slightly more accurate to the plane formed by these blades. All right, so hopefully now when I collide with it, it should react to my collision and have some, maybe not fully physically accurate behavior, but this is something you can play around with and maybe add some more dynamic feel into objects in a scene. All right, so this is hinge joint. The next one I want to show you is a slingshot. All right, so the slingshot, I decided to design it around the spring joint. So here I reused this poles here, and I added I connected these two poles with the spring joint with this ball here, right? So when I try to move it away and I release it, it will shoot a bullet, right? So this is the design I want. Now, the thing I didn't show you is that I added a script that allows me to kind of select objects and drag and drop them in my game view. So the script that I added, let me show you how it works on these llamas here. So it's basically, I call it draggable. So it will allow me to drag these objects around. Okay, so this draggable, basically if I click and drag any object here, it's going to move them with physics. This is something I use very often, and let me show you how the script looks like. So I have this draggable manager on update, so this is going to happen every frame. I'm checking if with the raycast, I basically perform a raycast and I check if I clicked on any rigid body. If I clicked on that rigid body, I save the distance from my camera to that rigid body. Distance in the Z direction. Okay, and then on every update, I'm basically getting the screen position of my mouse. I create a vector free and get a screen position X and Y, and I pass that distance that I recorded before as the Z parameter. Then I convert from my position from the screen space to the world space, so that when I started to drag my object with, let's say, distance 10, it's going to always stay 10 units away from my camera. All right, so that's basically it. And I record that position, my target position, and then in my fixed update, I check if I use physics. Then I calculate the delta between my current position and the target position. Based on that, I get the target velocity. I clamp it a little bit, and then I actually directly apply the velocity to my rigid body. So this is exactly the same I do here with my slingshot. I'm grabbing that object and I'm moving it in my camera space, right? So let me show that again. So this is, let me bring the mouse here. This is what I can do, right? I can grab it, move it away. It's moving according to physics. And when I release it, the spring joint will basically make this kind of elastic movement. What you can notice is that this rock here, this projectile, it stays always connected to my slingshot, and the thing that's spawning the bullet is a kind of a trick that I did here. So in my slingshot, I attached a script with a trigger area. All right, so if I notice that my rock, this stone, right, from the slingshot, if it enters the trigger area, I'm going to capture that moment here in on trigger enter, and I'm basically going to instantiate a new projectile and add a velocity that's equal exactly to the velocity of the this object attached to my spring joint. All right, so this is the slingshot setup I have. The spring joint itself is very simple. So on each light post, I have this kinematic rigid body that has a spring joint on it, and it's connected to my stone. The stone, as far as I remember, its mass is 10 kilograms. That's why I had to add quite a lot of springiness to the joint. If I make it lower, maybe around 10, you can see that there's not enough force to kind of push it back, and there's a lot of inertia here. So if your objects are heavy, make sure that you add enough springiness to it. Alright, you might also find that, you know, the springiness is a little bit too much, and my trick for that is to add some drag to your rigid body. So if you add slightly higher drag, and then this simulation is going to stabilize a little bit faster. Alright, so this is my slingshot. The next one I want to show you, this is something I use in multiple games. So here I have this rope that I can use. It's kind of like a wrecking ball scenario. Okay, so I have this very heavy object attached to it, and I can move it to kind of destroy my environment. So this is a little bit tricky to set up, and if you try to create setup like this with a spring joint, I'm afraid that you might fail with that. And let me show you how it's set up here. So for this chain, for the wrecking ball and ropes and any situation like this, what's more stable than any of the like hinge joints, spring joints, is something that we call a configurable joint. And this configurable joint has much more to it. You can basically restrict motion in an axis. You can restrict angular motion in X, Y, and Z. By default they are set to 3, but you can lock them so they don't move completely, or you can limit them to some certain values. Alright, so before I progress to this wrecking ball, because this one is quite advanced, I'm going to start with the dummy. So the dummy here, it has just one pivot point down here at the bottom, and this is just a kinematic rigid body, and it's connected to this dynamic object here. Alright, and now first I need to specify the axis, and the axis, this will become like a local axis for my object. I'm going to move everything around X and Z. So here I set it to 0, 1, 0, so that when I will be referring here to Y and Z, this will be my X and Z axis. I set the X, Y, and Z motion to locked, so it's not going to move in any of these directions. But I set my angular motion to the limited. Okay, and how can I make it to come back after I shoot it? So angular motion is set to limited. Then for each of the angular axis X, Y, and Z, I can set the drive. So there's this is for the motion. For the angular X, Y, and Z, I can actually set the position spring and position damper. So spring will add this force that will bring it back to the original state, and damper will slow down this process. So yeah, there are quite a lot of toggles and different parameters that you can set here, so I'm not going to go through all of them. I recommend that you go to the documentation and check it yourself. But for this setup, for the chain, this one is actually created through instantiating separate segments of the line. So here I instantiate objects that are connected together with the configurable joint. So each lower element is connected to the higher one. So here's the segment 0 is connected to the beginning of the chain. Segment 1 is connected to the one above, and so on and so on. So it's done this way here, and I actually use the script to do that because it would be too difficult to make it by hand. So I have this connect bodies method that's used to connect two rigid bodies together. So first, in my start method, I'm generating the chain by instantiating all these different points in my chain, in my rope. And after I instantiate them, after they all have rigid body, then I add them to a global list, and I iterate through this global list to connect each pair together with this configurable joint. And if you try to do this yourself, what you might find is that, you know, when you try to move it, it will be very jerky, and it's not going to move very smooth. So I think the key here, if you want to move a rope or anything like that, is to move it with physics. So back in this draggable script that I have, I'm going to make it move not with physics. I'm going to modify the position directly, and it's going to break entirely my simulation. So this is one thing. When you have connected configurable joints, you always want to use physics to move them around. You don't want to modify the position directly. Another thing I find quite useful is, let me add this draggable script to my wrecking ball so I can move it around. One important thing here is that you can see when I try to drag it too far away, the movement is restricted. And this is kind of my silver bullet for all kind of rope and chain scenarios, is when you create your chain of connected configurable joints, what you can actually do, you can set the, let me quickly find it, you can set the projection mode and set it to position and rotation. Let me show you how does it look like without projection mode enabled. So now every single configurable joint is not having a projection mode. So let me show you how the simulation will look now. You can see that the movement is very jerky. It's becoming immediately unstable. And when we reach unsolvable scenarios like here, right? My distance is way too far for the physics simulation to stabilize. So our physics simulation can't really find a stable position here, right? So what this projection thing does to our simulation, the projection mode here, when we set it to position and rotation, let me do this for the script. Projection mode, position and rotation. what this one does is it looks for, how can I describe it? It tries to find the closest solvable position, and it snaps the position back to the correct one, right? So we can't reach this kind of unsolvable scenarios now, both for the positional rotation. So it kind of restricts movement of our joint, but then the simulation is very stable, and almost never I can reach this kind of craziness that I just shown you, right? So my silver bullet for joints and chains is to use the projection mode. So this is the chain. One important thing to note is that any sort of chains, they don't like when you're, so I just very quickly mentioned that each of the segments, they are also rigid bodies, right, connected together with configurable joints. So what really breaks the simulation is when the mass of connected rigid bodies, if the ratio between them is greater than 1 to 10. So here I did something I shouldn't do. So my wrecking ball has 30 kilograms. So with this kind of scenarios, my simulation is not really stable. The ratio should be at most 1 to 10, right? So if my segments in a chain that I have here, if their mass is 0.5, then the connected rigid body, its mass shouldn't be greater than 10 times, because then, again, if we wouldn't enable this projection mode, the situation will become a little bit crazy and unstable, right? So you usually want to make sure that every rigid body in your chain, that the ratio of the mass is not too big. But you can also tweak that if you haven't done it with your rigid body setup. There is a mass scale here that can actually scale the mass of the connected rigid body. So you can scale either way, either the one connected to the joint or the one that's applied on you. So the mass scale and connected mass scale, these are the two variables that you can use to modify the connected mass in the joint. All right, so yeah, you can use this kind of scripts to quickly create ropes and chains to your simulation. And you can get some interesting effects with that. The final thing I want to show you, sorry, we are running out of time. The final thing I want to show you is the Ragdoll generation. So Ragdoll is this thing that allows us to, let me find the original object. The Ragdoll is this thing that allows us to automatically add joints to our object, and the joints are going to be automatically configured, as well as rigid bodies. And the Unity tool is going to automatically connect them and set the appropriate values for us. So to do that, you need to add your humanoid character, and you have to basically right click, go to 3D object, Ragdoll, and it's going to bring this kind of create Ragdoll tool. And here, I'm not going to do this live now because we are running out of time, but basically you just drag and drop hips, and so here it's named pelvis, left hip, and you just drag and drop all these different bones that you have on your character, and then you just create. Okay, so I'm going to skip this part because it takes some time. But after it's done, Unity will basically create this nice capsule colliders, the box collider for the chest, and the sphere collider for the head. So the default values, I find them to be very, very nice. I can't complain too much about them. So let me press play now, and you can see that. Sorry, where is it? You can see that now this character that we have is reacting to physics. All right. What I also did, I added my draggable script. Right, so you can see that on the hands, on the head, and on legs. I added this draggable script so I can drag it according to the camera, and you can create some like really goofy behaviors by doing that. You can like put him here in this carriage. Making him kind of chill here. You can move him around, grab him by the leg, by the arm, and yeah. You can create some interesting physics scenarios with the Ragdoll. And again, if you would move it with not with physics, because right now I'm using this draggable script that I created. I'm moving this by modifying the velocity. If you would move it by modifying the position, the simulation could become a little bit unstable. Actually, it would become unstable right away. So make sure that for the joints and rigid bodies, you always move them using add force, or if you know what you're doing, you can use the modify velocity. Also make sure that you clamp the maximum velocity, because again, although it looks quite stable now, if I try to move it like really fast, there might be some instabilities. And the same rules apply as with the configurable joint. So if you have your character joint, make sure that you enable the projection, so that when the simulation will reach some kind of unsolvable cases, it can snap back to the correct position. Alright, so that's pretty much it for the editor part. Let me switch back to my presentation. So just very quickly to sum up some of the final thoughts. If you want your physics simulation to be stable, make sure that you keep your velocities low, because if things with rigid bodies go too fast, they might go through the obstacles, your joints might not be connected together anymore. Also, it's important to understand the collision detection and interpolation to make your rigid bodies collide correctly with the physical objects in a scene with colliders, and use proper interpolation to make things appear and render correctly in a screen. Then avoid some unsolvable situations like I shown you, where maybe you have joint and you pull object in two directions apart and you reach this unsolvable scenario. You should by design avoid them. Configurable joints, they are the most complex one, but they allow you to configure every single thing in your joint. So if you want to create like a chain or a rope, the configurable joint is a way to go. Also for the joints, make sure that you keep the 1:10 mass ratio. Otherwise, if you attach a huge object to a smaller one, there might be some instabilities. And also, final note, it's always better to update your rigid bodies in a fixed update, not in the update, so that it's synchronized with the physics update loop. Before I go to the Q&A section, last week we released this really cool prototype series. This one is about physics, so it's called Physics Playground for camera spawning. So if you are new to physics, this is like a playground project that will walk you through and show you some very simple physics scenarios that you can use to learn about how physics in Unity works. So feel free to go to this YouTube. It's our official YouTube channel. Feel free to go there and check this one out because it's really, really informative and it's great for beginners. On our Unity Learn, we also have this Catapult Physics project. So this one will kind of walk you through how to apply forces and energy to your rigid bodies. So if you haven't checked out the Unity Learn yet, I think I can really recommend that one because we have many cool tutorials and this is one of the best one about physics.